We also learned about the dot product between two vectors. Dot product or inner product. So if you have two vectors, let U be vector, for example, U1, U2, Un, and V be another vector, V1, V2, Vn, both in Euclidean space of dimension n, then you can define U dot V, which is basically U1, V1, plus U2, V2, plus the rest of the elements, Un, Vn. And it had some properties, as you remember. It's commutative. So U dot V is the same as V dot U. You can also distribute the dot product over the sum of two vectors. U dot V plus U dot W. If you have dot product between two vectors, you have a scalar multiplication, which can be just written as the following. So C multiplied by the dot product is basically CU dot V, or you can write it as U dot CV. So you can just have the scalar multiplication for the first vector or for the second vector. It doesn't change the outcome. Or if I find the dot product between a vector and itself, I'm basically finding the magnitude of that vector and raising it to the second power. This one is super easy. If I find the dot product between a vector, it is V1 times V1 plus V2 times V2 plus Vn times Vn, which is V1 squared, V2 squared plus Vn squared, which is basically square root of V1 squared plus V2 squared plus Vn squared to the second power. But what is this? By definition, we learned that this is the magnitude. This is the magnitude of vector V, and you're raising that to the second power. So the dot product between a vector and itself is nothing but the magnitude of that vector raising to the second power. And number 5, the dot product between a vector and itself is always positive, or if it's zero vector, is going to be 0. So V dot V is 0 if and only if you have 0 vector.